Well, so what do we do about the complex eigenvalues case? In other words, we're trying to solve a system. We find eigenvalues of a matrix, and they are imaginary numbers. It would really be nice if we could come up with real values for the solution of the system that has real values. It would be extra nice if we could somehow wind up doing that. And this theorem, solutions corresponding to complex eigenvalues, actually this theorem maybe should be titled real solutions corresponding to complex eigenvalues. That would make everyone happy. But that's what this is about. Anyway, let A be a coefficient matrix having real entries of the homogeneous system of differential equations. This one. And assume that there is a complex number eigenvalue, maybe I should say imaginary number, eigenvalue z equals a plus bi with a corresponding eigenvector k. Then both k e to the zt and k sub c, now that means the conjugate of that vector k, so all the entries that look like a plus bi will be a minus bi, and then times e to the conjugate of z times t. They will be linearly independent solutions to our homogeneous system, and that's interesting, and that we can eventually work out so that it has only real numbered, real valued function solutions. Yes, that will make us happy when that happens. So what will we wind up doing? Well, it's kind of a cool thing. We'll wind up saying the conjugate, we will wind up using the same trick we used back in Unit 2 when we had second order linear differential equations that had complex solutions to the characteristic equation. It requires a little manipulation, but isn't too hard. Recall the Maclaurin series for e to the I theta is cosine of theta plus I times the sine of theta, which is a beautiful theorem in mathematics called the Euler formula. Okay? So just to show you why that's true, e to the x, you should know the Maclaurin series for that. You've probably seen it before. And sine of x, you can work this out, or maybe you've seen it before. And the cosine of x, you've worked that out, or you can, you've either worked it out before or seen it before. Anyway, e to the I theta, just replace all these x's with I times theta. But then raise I to the second power, you get -1. Raise I to the third power, you get -I. Raise I to the fourth power, you get 1. Raise I to the fifth power, you get I. And so here's a way of writing all that. But then see, every other term has an I in it, so let's factor those terms out with the I, and the terms that don't have the I, we'll factor them out to the front. Notice what we have here. I don't have the complete thing because it's infinite after all. But that's just cosine of theta, and this part, each term that had an I in it is just sine of theta, so therefore e to the I theta is cosine of theta plus I times the sine of theta. Pretty cool.